Recording. Okay. Yeah, this is our last course, and this weekend I marked the midterm exams, and I would like to share my some of my views with you. However, you are only now 4 students in our classroom. Very few of you. It's already 49 students supposed to be. Um, First of all, peak value and RMS value. Um, this is a major setback or major problem. Uh, if you are calculating the output voltage, you have to use the peak value over there. So you have to convert the RMS value. Most of the classroom have done that. And now also, yesterday I talked with some of your classmates. I asked them, "Can you see your exam paper?" They said, "No." He said one person. He said, "No, I can't." I said, "Why don't you open up so you can see your own exam paper in OLearn system? Probably you already know that. Not only seeing the mark you have got. The mark is since the weight is 30%, so 30% weight, according to 30%, you get the mark. One thing is also a problem, but this is I'm going to share with the when all the students attended. Now uh, as you know, I generally start with the revision of last week's discussion. We we start with inverters, which is called DC to AC converter, which is widely used in industry, in communications circuits, in power electronic applications, everywhere. Inverter, and also the motor control. We use inverters, and for motor control, we for electric vehicles, for example, or in the industry, there are a lot of motor controls over there. And of course, you are aware of the big trend that uh, big trend that electrification is occurring in particularly the transportation business. Therefore, when you graduated, you are going to and also join the industry or form your own company. The electric vehicle business is going to be continually rising, or exponentially rising rather. Therefore, a lot of jobs would be available in that area. Some basic functions are just reviewed here. You can see that power is always voltage, current, and the angle between cosine of the angle between those. Of course, voltage is sinusoidal or non-sinusoidal, might be current as well. Therefore, you have to be careful. But assume that these are fundamental components. So that is the equation valid. And also, if you have a resistive load, that means theta is equal to 0. So you have the power equation like this one. And also AC input power of the inverter is the RMS value of the voltage and the RMS value of the current. So I'm sorry. I'm sorry, I made a mistake. The AC, this is a, just wait, just wait. In order to avoid that kind of mistakes, we have to be careful. AC, AC is always, I'm going to take my special pen for my tablet. Actually, we have that is our that's our inverter. This is a VDC actually. So that current AC input power, that current here is IS, and the voltage here is also Vs plus and minus. However, here either single phase or three phase, we have an AC waveform. Although it's not very good, it's not very good means it's not pure sinusoidal, but we have output. So for input, you can see that AC input means RMS value, sorry, the average input voltage and input current is going to be input power of it. Bu AC lafı tabi burada Muhammed'i eleştiriyorum. Beni bile yanılttı. Öğrenciyi I also be mistaken by seeing AC here. Probably most of the students would be interpret that one as if it's a DC one. It's not AC. However, the RMS ripple content of the input current, of course, the input current is not sinusoidal. So we are going to see that the input of the, that's why they call it AC here. The input here, current is not sinusoidal anymore. Or for example, that kind of current we draw. For resistive load, current is going to be something like this, similar to voltage, IS. So that means it has a fundamental component, first component, and then third component, and fifth component, so it's all together. This is the current waveform. So it's not sinusoidal anymore, input current. Therefore, it has also fundamental component and other components as well. Of course, it has a DC component as well. But if it's a symmetrical, there is no DC component. Plus and minus becomes 0. So let's come back, just review our definition. The ripple, I already have given those equations to you. I'm just repeating it. square of the ripple is equal to square of the DC and RMS. One of them is RMS, II, and this one is a DC, an average value. So it has that is the definition of ripple. And ripple factor of the input current is equal to this, and the harmonic factor of the output is defined as that one. So individual harmonics, for example, fifth harmonics over fundamental harmonics. So you have to know the Fourier analysis. So that means, and also total harmonic distortion is defined like this. Don't forget that there's a square root here. Okay. Square of the harmonics divided by fundamental. Total square of harmonics divided by, get the square root of it, divided by harmonics, the fundamental. This, I omit that one. However, one thing is clear, that if you fire Q1, the current is going to flow through that line. Şöyle çizeyim. So that point receives a positive one, and then when you fire the bottom one, then it's going to get a different direction. So I omit that one example, but one thing I don't want to omit is the Fourier analysis. If you apply the Fourier analysis of that waveform, Fourier analysis of this waveform, square wave, you are going to obtain, since half of the voltage comes to this, you obtain this function. Only odd harmonics. The fundamental, third, fifth, and however the amplitude is 2 times Vs over m pi. Fundamental component is equal to 2 times Vs over to this one. So I omit that one. Come to, and also current equation is something like this. And the fundamental, the power, actually, that power equation is enough for you. However, if you have third harmonic current and third harmonic voltage, then of course you might have power for the third harmonics as well. But to forget about that one. Assume that power is equal fundamental voltage, fundamental current, and the angle between those. That is the one we discussed a lot. This is a bridge inverter. I repeat, we have already 6 students in our classroom. We have, this one is a bridge, and that is the waveform you get. We talked a lot about this one last week. I'm just warming up the course. That is the waveform. typical square waveform. And when you analyze this waveform, you end up with the Fourier analysis. For certain periods of time, Q1 and Q2 are conducting. Another period of time, Q3 and Q5 were conducting. Q3 and Q4 were conducting. I repeat from very beginning. For the first part, Q1 and Q2 are conducting together, so current is flowing through that line. Başka bir renkle göstereceğim, current'ı karışmasın. Kırmızıyla kare. Current is flowing through that network. And the positive voltage comes positive voltage, positive and negative here. Positive voltage comes to the A point, so we obtain that positive part. It's not so simple. We have discussed that one last week. If your network is inductive, inductive means you have L and R. If that kind of equation we have, then current is going to lagging. Therefore, that kind of current waveform you are obtaining for inductive loads. Now, this is fundamental component, by the way. However, we have already analyzed that there are some peculiar parts where the current, for example, between in this direction for violet color direction, here at this point, current is continuing since you store energy in your inductance. Therefore, you cannot reverse it. So what are you going to do when you put Q1 and Q2 off? What's going to happen? This current, that current here in inductance, is going to divert its direction back to the source. But it's not going to change in inductance. Inductance current remains the same. So that's why for this part, D1 and D2, bakın, for this part, D1 and D2, and for that part, D3 and D4. Yani burada, for this part, D3 and D4 are conducting. So that basic principles, we just remember what we have discussed last week, just to refresh our memories. But now we are going to evaluate those waveforms. Now, the RMS output voltage. When you employ RMS, what does it mean? Root means square. You first get the square of the function, then you get the average value of this, mean value, and then square root of it. Here, square of the function, get the average, then get the square root of it, and it's equal to the peak of the DC volt, not peak, the DC value equal to the DC voltage. That one. Can you see that? DC voltage. When you employ Fourier analysis, however, that is very important. You remember that it was 2 for the half wave, but full wave, that's the fundamental equation. Bu önemli bir equation çocuklar. So that means n equal 1, n is a harmonic order. Yazdım mı daha evvel bilmiyorum ama I'm going to write again. N harmonic order. And 1, 3, 5, 7, 9, 11, 13. So it goes like this. N 7, 9, 11, 13. So it goes like this. N equal 1 is called fundamental. Fundamental. The others are harmonics. So these are harmonics. But n equal 1 is the fundamental one. So if you analyze this one, you are going to obtain a waveform like this. Galiba yazdım bunu ama 4Vs over pi times sine omega t plus 4Vs over pi times bölü 3 harmonic order times sine 3 omega t plus 4Vs times pi times 5 sine 5 omega t plus. So this is a kind of function is this. So that one is the fundamental and the rest is the harmonics. So this is important, okay? Then in order to evaluate those, fundamental component is RMS value. Buraya hemen bir RMS demeyi unutmayalım kocaman. RMS value, we divide it by square root 2, since if the relationship between maximum value and the RMS value for the sinusoidal functions, in exam papers I made a lot of mistakes for this one. If waveform is not sinusoidal, you have to calculate the RMS value. You can't just easily divide by square root 2. For only the sinusoidal relationship, that one. For RMS value, we divide by square root 2. Okay? And then we obtain that fundamental is equal to 0.9 times Vs. If we have an impedance, of course, for impedance, current is equal to voltage divided by the impedance amplitude, but it's a function of n, the harmonic order. Since you have an inductance in your load, your inductance is increasing with the harmonic value. For example, for the third harmonics, your inductance should be multiplied with 3. And for the fifth harmonics, it should be multiplied by 5. It's obviously can be seen here. I hope you understand that one. And also angle, you have to define each angle differently. So this is a current waveform. Impedance, voltage divided by impedance times sine, and also the phase shift between current and voltage. Evet. Galiba benzer. Bunu hiç sevmiyorum çocuklar. Bunun denklemi uzun. Bunu atlayayım. Şimdi, what is the operational principles of those? We already discussed that we put S1 and S2 on, S1 and S2 on, and the others off. Then S3 and S4 on, and the others off. And also both are with, baştan alıyorum. S1 and S2 on, S4 and S3 off, of course. But here S4 and S3 on, and S1 and S2. So some of them, the switches at the end in a, let's say, in logic circuit is defined like this. But that one is more illustrative. If you study this part, you can see that whatever I say in words, S1 and S2, if S1 and S2 on, of course, D1 and D2 uh, for the negative current, D1 and D2 is possible. Şuraya bakın, bu en güzel anlatılan yer şurası çocuklar. Evet, burayı ben çorbaya çevirmişim. Bir saniye. Burası. Böyle yarım olmaz bu ama. That is not equal like this. This kind of figures only obtained with very high inductance or almost no resistance case. This one is the realistic case. So for this part, D1 and D2, and for that part, this part, D3 and D4 are on, and the rest are the normal transistors are on with couples. This is what single phase is all about. And the current, of course, waveform is going to be something like this, but the fundamental of the current could be calculated like that one. You can see that this part, the diodes are conducting, and also that part also diodes are conducting. Gidiyoruz. Three phase. Şimdi bunu bir hemen atlayayım. İş çıkarmayayım. Buradan alacağım. Now we are starting again to three phase. We have just started this one, but I'm sure it wasn't good enough. So we have to clearly understand what's going on here. It's already half an hour I started, so I'm going to take attendance. I don't know why students are not attending the course, since this is an important business. Thank you for Raid, Muhammed Abdülvahid, Mahmut Ramadan, Halil Hatim, Hüseyin Mahir, Hamza Muhammed, Ahmet Orabi, and Abdulbari Abdul Samet. Thank you. So I'll just take your names. Just a moment, please. I'm going to put your names in my attendance list. I remember that when I was at Istanbul Technical University, sometimes the class was 80 students or something like this, and everybody was there in 9 o'clock in the morning. Now it's almost more than half an hour past. and only 20% of the students are attending the course. Just a moment, please. I'm just okay. I've taken your names so we can continue our course. Now, load is actually connected to those points. These 3 points are connected to the load. So if I take those loads like this, so that one EA, that one EB, that one is EC. Reference voltage points there. LA, LB, and LC. RA, RB, and RC. So three-phase load is connected to those points. Then when you put the first interval, I'm going to put the first interval. For the first interval, you can see that this one, G1, given gate signal, therefore we send the current to that one is conducting. That one is conducting. And also we have sent G5. We also send signal current to phase C, and that might be an electric motor, for example. And also we send the signal to, for those interval, for G6. G6 is conducting, therefore its current is in this direction. So actually this voltage source Vs plus and minus Vs supply the current like this, and that current returns through is it the only one you can't see the slide? Someone says he can't see the slide. The rest are seeing. Put it off and put it on again. Probably there is something wrong with your system. Abdul Bari. So we are getting current. Okay, good, Abdul Bari. That distance teaching is something very bad for me. When I go to the, for example, walking on the campus, going to, for example, lunch, some students are saying hello, teacher, or hello, professor, and things like this. But yeah, since you can see me, but unfortunately I can't see you. I can only learn about your names. Uh, However, your faces, I don't know. So this is the current, all right? So half of the current is coming. So this is the current, all right? So half of the current is coming from Q1. The other part is coming from Q2, and the other one is going back through Q6. Only for this interval. So that interval. For the next interval, another picture is going. So what we are now looking at, the waveform, is this one. You can see that. VAB, the voltage between A and B, that one is A. This point is A. This point is B. And that point is C. So VAB is equal bakın A noktası, A point is connected to positive, B point is connected to negative, neglecting the voltage drop of those, is exactly equal to supply Vs. It's here. Is equal to Vs. So you can see that. The waveform is something like this. Şimdi current rengi değiştireyim burada artık. So VAB is going to be something like this. But at this interval, şu intervala bir bakalım. Şu intervala bir bakalım. Onu da blue ile göstereyim. For this interval, bakın bakalım ne oluyor. Still, first switch is on, and also second switch is on, and third switch is on. So first switch is on, second switch is on. Nerede second switch? Burada. Şekli karıştırmasın diye çizmiyorum. First switch is on. A point is connected to this point. A is still connected, but B point, since D3 is also conducting, Q3 is conducting, B point is also connected to that point. So A, for look at the blue signs here, A is connected here. Şuraya bağlı. Buna karşılık B is also connected there. The same voltage they are conducting. Therefore, VAB is 0. You can see that VAB is 0 here. We are concentrating on VAB, and for the next period, then you have gene violet color'a döneyim. Then next period, you get that waveform. Blue. No. Another 0 period. So at the end, your waveform is going to be something like this. Some 0 parts and some, it's a kind of square wave, quasi square wave. Quasi square wave. And also the other phases might have quasi square wave as well. Now we are in the different situation. We have to employ the Fourier analysis for this one. But what about these are the line voltages, but we all know that are system either connected star or delta. I just explained this for the star connection. Either your system might be as simple as like this, star connected, or for star connected or delta connected. So you remember your examination paper. I asked the rectifier, and I said, why don't you solve? I gave 10 points to draw. So I come back to the examination question. I'm very much disappointed. Some people produce some funny things. I understand that you either have asked the solution to ChatGTP, or someone discovered that stupid method and then send it to others, and everybody used a very funny shapes. I don't even understand those shapes, and I'm 100% sure that those students who draw those, not the curve, something like this, it was. So if you open up your examination paper, you are going to see that the answer all those. But there are some students who answer it. I'm very much glad that That was the answer should be. As far as I can remember, it was delta. This is the primary transformer. A, B, C. So VAB is a line. 380 volt. RMS by the way. Şimdi bu 380. That one 380. This one 380. These are the transformer legs. You might write like this. So these are transformer legs. Now, similar transformer we are going to establish here. One leg is parallel to this. The other leg is parallel to that. The other leg is parallel to that. And the line there and also we have a rectifier here. Three-phase rectifier. Load is there. This is the load current, 100 amps. This is the load current. 1, 3, 5, 4, 2, 6 or 2, 6, 2. I don't know. Doesn't matter. Şimdi şu noktayı diyelim ki buraya bağladın. Bunu buraya bağladın. Ya da bunu getirdin. You connected here. Bunu getirdin. Connected there. Bunu da getirdin. Connected here. That's it. Şimdi that voltage is 380 volt. Since n equal 1 or A equal 1 transformation ratio. A diyeyim buna. Turn ratio is 1. So that voltage is, this is A prime. This is, let's say, C prime. Bu da B prime olsun. B prime olsun. So V A prime B prime is equal to square root 3 times 380. But peak value VDC 3 over pi V line max. So 3 over 3 pi times line voltage is square root 3 times 380. Max value square root 2. These are RMS values. So you have to multiply with it. That's so simple. As long as I see that one, I gave 10 marks. Sometimes even I couldn't see what, for example, the current here is actually could be calculated when you analyze the RMS value, you are going to obtain that one. Even I didn't look at the current here. Current is not 100 here. Current is equal, ezbere yazmayı hiç sevmem. 100'tır. Neden? Since you are going to take the current waveform, so the source switches, since your 100 volt is a load current, but those switches are sharing the waveform like this. Başka renkle çizeyim onu. So this is Vs diyelim. Vs diyelim buna. Vs square plus 0 square plus Vs square over 3 karekök. 2 Vs 2 Vs square over 3. That's why. Nerede o? Ha, şu. Sorry, bu IS, bu VS dedim ya. I'm sorry. I made a mistake. This is the waveform of IS. And this is the RMS value of this one, which is equal. Even if you don't give that one, I gave 10 marks. Or sometimes I just couldn't see those 380s here yet. So that's so simple. 10 marks. Okay. Let's come back to original file. Just a moment, please. I open a different file. IS RMS bu çocuklar. RMS. If waveform, I repeat, if waveform is not sinusoidal, then you can't use square root 2. You have to calculate the RMS value. Either open up the function or my easiest way. That method is my easiest way. If you have a square wave like this or quasi-square wave, you just get it this function. Anyway, I come back to original course material. I know you are tired now a little bit. We have only 12 students in our classroom. That's the one we have. For example, if you want to, now you can analyze that waveform. What's the RMS value of this pink colored waveform? It's the same. Square of this one. Two half zeros here, so 1 0 square, and another square, which is square since it becomes positive, since negative function square of it becomes positive. Then it's square root 2 over square root 3 times Vs, the RMS value of this waveform. Anyway, I'm going to give the break. I'm going to have a coffee. $10:15 break. Okay. All the best. Sorry for being late. Yes, we have already seen the operational principles of the three-phase inverter. But one thing I must remind you that if look at the gate signals, 180 degree you are giving gate signal to each thyristor or to each transistor. So that is the 180 gating policy, or 180 policy it's called. There are other policies as well. The other one is 120 degree conducting period. Okay, you can see the waveforms for 180 conduction. So we obtain three-phase square wave waveforms like this. One of them is the pink color, and the other one is, let's say, blue one. That's the one. And the other one is going to be like this one. These are line voltages. Don't forget, line voltages, okay? Now, let's move. But that system might be star or delta, the load. If the load is Y connected, the supply current is going to be, I'm sorry, the supply voltage phase to neutral voltage would be different. So let's say this is the case, and that is the neutral line, and that is N. So VAN, that one is VAN. Of course, different than we already know the line voltages. So what about the simple V phase voltages would be? For each case, your system is connected either like this, two phases. For example, the one I explained, two phases are parallel connected, the rest one is seriously connected to third phase. Remember that A and C was parallel connected. That was the figure still there. That's the one. You can see that phase C and phase A are connected, and the reverse current is flowing through B. This one is directly connected to B point. So that is the case. Did you understand that? That is the case. In that case, so when you calculate VAN, the node point, can you see the node point here? Star connected, node point here. VAN is calculated and it's obtained that VS over 3. Şimdi onu göstereceğim size. Kitabın kopyasını koydum ki çalışırken bir lazım olursa işte tam anlayın diye. R equivalent is equal R plus R over 2. Geri dönüyorum. R equivalent burası that one is hepsini yapmayacağım çocuklar. Zamanımız dar. R1, R2. Sorry about that. Gene kalem. So the equivalent of this one, equivalent of that one is R over 2, since two parallel is connected. Then plus R equivalent here. R plus R over 2, which is equal to 3 over 2R. Burayı söylüyorum. For this case. So I'm sorry. I1 is equal Y Vs over R2, R equivalent, which is equal to this. So VAN is equal VCN is equal I1 R over 2. Bakın göstereceğim şimdi. I1'ı göstereceğim hemen. I'm sorry. I1 is the one. So I1 neye eşit? Bunun için I1 is equal to Vs over R equivalent I1 is equal to 2 bölü 3 2 bölü 3 Vs over R. 3 bölü 2 idi bu. Dolayısıyla 2 yukarı bakayım kontrol edeyim. 2 bölü 3 Vs over R. Peki şey ne? VAN ne? VAN is equal to I1 times R over 2. VAN A point here, AN is equal to I1 1 over 2 I1 therefore VAN is equal de R var burada. R'yi unuttum. Vs bölü 3 çıkar. Şurayı bulduk. We obtained this part. So if you continue in the same manner for the second part and the third part, if you analyze each individual like this one, then you are going to obtain this waveform for phase A. That is, of course, is much better than the quasi-square wave. For phase A, we obtain that waveform. For phase B, it's rather 120-degree phase shifted, the same waveform, but 120-degree lagging, phase B. These are neutral, phase to neutral functions. Bu hatta böyle gidiyor ya. Bunu burada bırakıyor ama. Böyle doğru değil bu. Yani böyle devam etmek lazım. Evet. Phase C has got this waveform. Another 120-degree phase shift with respect to blue, or 120-degree leading with respect to A, the red one. Tamam. Yani şurada bir Vs over 3 var. Şu da 2 Vs over 3 top. Evet. Yeter bu kadar bu. Yürüyelim bakalım ne göreceğiz. Now, VAB, the instantaneous line-to-line voltage VAB for Y connected load, yani burasının aynısı. The same as this one. Line connected VAB here, you can see that. The analysis of this one here, you can see that. The analysis of that one. But for star connected system, sorry, is equal to this. Follow me. 4 Vs NP n pi sine n pi over 2 sine n pi over 3 times, burası, this one is amplitude. Bakın, amplitude. I'm not saying RMS. So if you divide it by square root 2, you get the RMS value. Since this is a Fourier analysis and it is yeşil istemem. Yeşili fazlar için kullanıyorum. Demek ki turkuaz veyahut da pink filan gibi bir şey kullanacağız. I'm going to use a pink color. That's right. So that part peak. Rest of it is a sinusoidal. Sine n omega t over pi over 6. Burada da bir hatası var ha. Buraya bir en koyması lazımdı. Neyse. Yani formu genel olarak doğru. So for phase BC you have the same curve but there is a phase shift and that one is the phase CA, there is a phase shift. Tamam, bu denklem doğru çocuklar. Buraya en koyması gerekmiyor. No need that one. So this one is only phase AB. These are line voltages. Line. Okay. But what is N here? If you put N equal 1 is fundamental and the rest third harmonics. If you put N equal 3, N equal 5 is a fifth harmonics, N equal 7 and so on. Continues like this. So let's go. That's right. What about the first one? Şimdi bu denklemi anlamanızı istiyorum çocuklar. Line voltages first fundamental component. Bakın yapacağım şimdi. Siyah bir kalem alayım elime. Ya da mavi de olabilir. Neyse siyah alayım. Şimdi neydi bu? N equal 1. Şu denklemi buradan bakalım. 4 Vs over Np N equal 1 4 Vs over pi N yerine 1 koydum. I put 1 for N times sine pi over 2 sine bir tane daha var. Bakıyorum buradan. Sine n pi over 3. Sine pi over 3. Şimdi burada ne eksik? Kim bulacak? RMS demiş. Demek ki başından bunu bir kere bir karekök 2'ye böleceksin. This one is peak. Of course, peak of a sinusoidal function. Therefore, if I divide by square root 2, then I get an RMS value. Devam edelim. Ne çıkıyor? Şu 4 Vs over pi square root 2 times var burada pi. Sonra ne kaldı? Sin pi over 2 1. Bu ne peki? Sin 60. Sin pi over 6 dursun böyle. Budur doğrusu. Yani Muhammed ille bayılıyor böyle şeylere. Bu tuhaf sayıları başına koyup kafa karıştırıyor. Bana kalırsa bu doğrusu böyle kalmalı. RMS value of the line to neutral voltages, bu line voltage line to neutral olduğu zaman line voltage'ı line VL'i divided by square root 3. Tamam mı? V phase is always is equal to V line over square root 3. That's all. Bitti. Şimdi there is another, that is the waveform. If you have neutral for star connected transformer, since the current is flowing, so I'm sorry, for star connected load, so this is the inverter. Biraz renk alalım artık ya, bu ne ya? A, B, sorry, C bu. Güzel olmadı. That point A, that point B, that point C. So this is the three-phase inverter. Okay. So then C anlaşılmıyor burada. Evet. Şimdi anlaşıldı herhalde. So that is the, if you analyze the waveform, you are going to obtain this kind of output. Waveform for LR type load. Giriyorum. There is another policy which gives you VAN, VBN, and VCN star connected. So that is the instantaneous phase voltages for a Y connected load. Bir önceki line to line voltage'tı bu denklemler. Şimdi gene star connected'ti. Değil mi? Gene it was star connected line to line voltages'dı. That one is star connected but line to neutral one. Just divided by square root 3. That's all. Nothing else. If the current then is going to be for phase A, for example, you are going to multiply omega with n here, the impedance, and of course there is always a number of order, harmonic order there, and this was the amplitude, you remember, and that is the sinusoidal part of it. Bu kadar zorlamayacağım şartları. Burada kalacağım. That is another policy. Remember that the gating signal was 180 degree, but now gating signal is becoming 120 degree only. So for that case, at a certain instant, bakın şu instant'ı çizeyim. Again, it's a 6-pulse rectifier. So these are the intervals. You can see that at the same interval, there is always 2 switches are conducting. So if you look at the inverter network, bakayım çizmiş mi? Hayır, çizmemiş. Geri dönüyorum. Ya da kendim çizeyim şuraya. Bir tanesini anlasanız yeter. So if you only, for example, this first interval here, this is the first interval. Only one, the first one, and biraz büyüteyim, gözüm görmüyor, 6 galiba. 6-1 is conducting. Evet, numaralanmaya bakacağım şimdi. Aynı numaralanmayı kullanayım. That's right. Evet. Buna ikinci second leg is a 6-1. So 4-6-2. Four, 6, 2, 1, 3, 5. Şimdi for this red one, the first is conducting. Therefore, kırmızı renge geçeceğim. First is conducting, current is flowing through the first one, going to the load, and then bakayım ne var başka. 6-1. Evet. 6 burada. Buradan geri dönüyor. Öbürü boş. Current is flowing and coming back to its source. Current is coming from the positive part. So VA neuter, this is the neuter point. I'm sorry. Hala silgide. Nerede yazıyor? So this is the neuter point. Third phase is not connected. Therefore VAN, you can see that it is on. So we have a quasi square wave obtained, and the Fourier analysis of those also, or similar argument here for each case, is solved. I'm not going to give you in detail. And the neutral phase voltages are represented. This part is a peak value, that part here. Peak value of VA max, maximum value, and the rest is the sinusoidal function variation, and the B phase is similar, C phase is similar, only difference those between, there is a phase shift between those. If it's a pi over 6, then this one is, if you put minus 1 over 2, sorry, minus 120 degree, you obtain pi over 2 here, and also minus 7 pi over 6 here as well. I think that's enough, since we have to look at the waveform you don't like. These waveforms we don't like. How could you control the voltage, and how could you reduce the harmonics? Then it's the method called PWM is employed. If you have those high frequency triangle waves and compare it with the reference signal, the intersection between those are defining the on periods. You can see that the waveform is divided, square wave is divided some 6, for example, 5 parts. Then if you increase the control signal above, it's going to approach, and if you touch here, it's going to be a complete square wave. But if you reduce it, that control or reference signal they call it, but it's a control signal. This one is, these triangles are carrier waves. High frequency is the better, but the frequency is also defined the number of pulses here. Higher the frequency, let's say, not very high. And if you reduce the control signal here, that those pulses become very narrow. That means RMS value goes down. I hope you understand that one. So you are comparing. This is one method. I'm not going to give details. These are given here. If it is necessary, you can use it. Harmonics. Another method is sinusoidal. I'm talking about the single phase. If you provide a control signal sinusoidal comparing with higher frequency square waves, you can see that I'm going to amplify that one. I wish you can understand this waveform. I don't want to discuss this one. That's much better. You can see that for those you are comparing this, these are carrier waveforms, these triangles, and that one is your reference waveform, or probably you may call it control signal. If you compare those, intersections will telling you the width of the pulses. Here you can see that on top the width are wider, and here the width are narrower. Therefore, produce a kind of waveform like this, wider in the middle and narrower in the corner or near to the end of those. Therefore, the PWM, this method is called PWM, pulse width modulation. This method is called, bakayım ismi vardır yukarıda, sinusoidal pulse width modulation. That's right, it's written here. Sinusoidal pulse width modulation. So you are actually comparing that waveform with those triangles. For example, it's white here, and then it's getting narrower. This is called sinusoidal pulse width modulation, still used. Another method, of course, Fourier analysis is given for those, and then the geri döneyim. Bir tanım vardı orada, onu vermek istiyorum. Starting from here, one method is this one, is multiple pulse width modulation. So the width of those are equal for this policy, and the average, output voltage, RMS value of the output voltage is equal to the delta is the width of those pulses and the p square root of it. I'm not going to prove this. However, also the coefficient of the Fourier could be calculated like this, and these are the distortion factor and also harmonic over RMS value are given. M is the modulation index. Bir yerde yazdım. Ha. That is the Fourier of the sinusoidal pulse width modulation system. You can see that N here is the harmonic order again. Burada. That is M is the modulation index. The ratio between triangle and the peak of the sinusoidal function. Gördüm bir yerde. Dur bakayım. That's right. It's given here. That's the modulation index. Evet, uzatmayacağım. It's our last course. We are not going to discuss in detail. This is also another PWM method. So you are providing different width triangles and sinusoidal comparison and obtain that kind of output. Today, the method for three-phase is the similar three-phase waveforms produced, okay? So phase A, biraz büyüteyim. Phase A, phase B, phase C, 120-degree phase shifted. They are compared with, again, those triangles and intersection points define that kind of waveform for each phase. For phase A, you are going to obtain that kind of waveform. This sinusoidal pulse width modulation is still popular, but these are the waveforms of three-phase networks. The method called space vector, I'm not going to teach, but don't forget, state space vector widely used in induction motor and synchronous motor control. If you are interested in the motor control business in the future, you are going to you have to learn the space vector method. We have no time to discuss it in detail, but the switches are digitally controlled with angles like this. These are the first, second, third, fourth, fifth, and sixth cases. So the switches are conducted accordingly, and then the better waveform is obtained. This is what space vector is all about. Burada bırakacağım çocuklar. Şimdi bir başka konuya geçeceğim ama gene bir küçük break vereyim. Sonra biraz konuşacağım sizinle. Sınıfta 14 kişi var. Space Vector ile ilgili yazdığım yazıyı bulayım. Orada kalayım. Lazım olursa çalışırsınız. If it is necessary. Bir dakika, buraya geçtik biz ya. That's right. this is an important PWM method. Now, I would like to talk to the examination. You know that examination is going to be face-to-face, and it's going to be open book. In order to become successful, you have to clear your mind. What rectifier is, or the before rectifier, we have covered some other topics as well. So those topics, for example, RL network, LC network, single switch examples. Then we worked about the rectifiers, uncontrolled, fully controlled, one phase, three phase bridge. Then we come to become a DC to DC converters. We worked hard on this one. You already know the buck converter, you already know the boost converter, you already know the buck boost converter. These are widely used in industry. And then we come to the inverter. And in inverter, we have seen 180 conducting period policy or 120 degree. So equations are already here. So you can look at it. But if I strongly suggest also to buy Muhammed Rashid's book, or there is a translation over this one for the Turkish students. The Turkish one translation is much cheaper. It might be a reference book for you in your future as well. Now the last topic we are going to use, but before we are getting, let's say, break here. Saat kaç? 5 geçiyor. 11 5 geçiyor. Evet. 11:16'da 10 minutes break. 11:17'de buluşalım. Break. Stupid. Okay. See you then. Hello again. Final topic. Final topic, which you might be faced with during your engineering life, is AC to AC conversion. I don't want to give you some misleading properties, but mainly AC to AC converter is something like this. We have an AC source here. If you put this is the basic principles of it. We have a source, reference point here is AC, so supply Vs here is equal Vm sine omega t, and we have back-to-back connected thyristors here. The first one, if you put, since we have a waveform like this, if you put the first T1, this is T1, T1 is going to conduct the waveform, and then if you put T2 here, when the voltage becomes negative, then of course we can use T2 here. So between 0 and pi, T1, and then between pi and 2 pi, T2 is operating. We can transfer that waveform T2, that waveform if the load is, if the load is R. If the load is R, so that there is no phase shift here, so that is the load current, I load. That is the load current flows through the load. But load cannot be always resistive. If you have, since the current is going to be, for this, my blue case, the current is going to be something like this. Amplitude of this one. The current of this one is going to be something like that. But this one is firing alpha is equal 0, alpha is equal 0, and alpha is equal pi. You are just transferring whatever you can see. whatever the input voltage is, you are just transferring it. But that is not the case. Since you put here thyristors, you can control the firing instant. Now, for example, this one is another voltage let's say control circuit. If I fire, that is actually this waveform. If you follow my cursor, please, that waveform is applied, and then at this point for alpha, you fire T1, and T1 is going to conduct this current, and then you wait at pi. So this is the that point is alpha, okay, and that point is pi plus alpha. You give a gate pulse to the first one, T1, and T1 is conducting, and whatever the voltage is, then you can see in the load terminal, and the current is proportional with those. But that is the current. So the output voltage is the current times R. VO, output voltage, so that is for example is the one. You get this one. Depends of the resistance. Bunu bırakın. Bunu bırakın. Şunu da bırakın. Sadece blue şu current'a bakın. You can control the current, so you can control the power. Power output is equal IO square, RMS value of course, RMS times R. So if you have a waveform like this, that waveform, then you are going to find the RMS current in order to calculate the power. That might be a resistance, for example, for heating purposes. You are controlling the heating, for example. Heater. The RMS value, since the voltage, dalga şeklini çizeceğim buraya. Buradan anlatacağım bir daha çocuklar. Bakın. Beş punto çok kalın. That one is Vs. Supply time. Okay. Now we are firing the current. We are firing at pi. Şurada bir alfada bunu fire edelim. Then current is going to be similar. Current'ı bırakalım önce bir. Load is resistive, tamam mı? Then this is pi. That is pi plus alpha. We again fired. So we actually sent this waveform to the load. So rest is 0. So this one is VOT. That one. Sorry. First day of our classroom, I also mentioned that one. I also draw those curves to you in February. The red one is VOT. What kind of waveform is this? It's alternating voltage. Alternating voltage. Since the average value is equal to 0, so there is no DC component in it. Positive part is equal to the negative part, since the waveform is symmetrical. So what we need to find the RMS value. RMS value, how could you find the RMS value? So VO RMS is equal to, get the square of the function. Follow my cursor, please. Follow my arrow, please. Get the square of the function. Function is equal to this. Vs is the RMS of the supply voltage. Therefore, square root 2 times is the peak one. This is the function. So square of this function. Get the average of it. And then get the square root of it. Root means square. So what are you going to do now? You are going to calculate it. We all know that sine square omega t is equal to 1 over 2 minus 1 over 2 cosine 2 omega t. Sığmadı. Right. So that is the one which is employed here. So 2 is going here, it becomes 4. So 1 over 2, 2 becomes here 4. And the 2 times 2 becomes 4 as well. Vs square is transferred to the outside of the, and pi is over there, times this one. So this one is equal omega t from alpha to pi, therefore pi minus alpha, and then minus this function. But for this function, the cosine pi is equal to cosine 2 2 pi is equal to 0. So only the alpha term remains. So but of course, this is a sine, cosine. When you get the integration, it's going to be sine function, and sine 2 alpha over 2, then you are going to end up with this equation. It's a famous AC to AC conversion equation. I might ask a question in the exam. Okay? I'm not sure, but I may ask a question in the exam for this example. There is a problem in your book. They say, how could you find the power factor? First, obtain the RMS value of the voltage, and then the resistance problem is here. Resistance is given. So if you delay angle is given, pi over 2, 3 pi over 2, so half only, then this is the solution. Can you really solve this problem? We have 20 students in our classroom. Can you really solve this problem? It's a simple example. You have a network like this. It's a AC to AC conversion. Simple. It's called AC chopper. Quite often, it's called AC chopper. And if you look at that one, the voltage is given, and firing angle is given, alpha is given, and it is asked that what is power and what is power factor. Input current, input voltage is sinusoidal. Input current is not, therefore it has to be calculated. So the output power and input power is calculated, and it is obtained that the output power over input apparent power, by the way, input apparent power. If you write in your examination paper as a power, volt times current is not power actually, it is apparent power. Okay? Power is only, there are two types of power. One of them is active power, which is actual power. The other one is reactive power. But this one is apparent power. It's a fundamental issue. So that is the equation. VO over VS, the power factor, and it's obtained. This one divided by that one is here. Bakayım başka ne var? An average thyristor current for each thyristor, of course. Şu denklemde. For here, for each thyristor current, half of the current is the positive current is flowing here, but the negative current is not. You can see from alpha to pi sinusoidal function, and then you can obtain the current as well. The RMS value of the thyristor current is also given. Obviously, you are for obtaining that one, you divide by the volt square over R square. So that is the RMS current, and this is the RMS current function. Buna gerek yok. That circuit is used for positive voltage. Bakın ne oluyor? Söyleyeyim size. for positive part, current is flowing. That's the way. As we all know that supply voltage, is sinusoidal. Let's assume that the positive part şöyle bir alfa seçtim. But here, since the voltage goes down to negative region, then for the negative region, that one is pi plus alpha. Then this portion is transferred, and if you neglect the voltage drop, the output function VO and the negative function, negative part is again VO, constitutes the complete output voltages. But in that case, for negative part, since voltage is negative, this negative voltage, since this function is half of the period is positive, the supply, I'm talking about supply voltage, half of the period is positive, blue one, another half is negative, the red one. What about the power direction? Can you predict the power direction? Since the current direction, as long as voltage is positive, current is positive. As long as voltage is negative, current is negative. Therefore, product is always the blue current and the red current are negative negative, and the positive positive multiplication always gives you the positive energy. I hope you understand that one. VT. Is it clear? Now I have a question. Why did we put those diodes here? In order to protect the short circuit. So if we are in the blue one, and if while the current was flowing in this direction, then the voltage becomes negative here, and the diode always protects. If you have an inductance in your load, it is difficult to convert the current direction. Therefore, until the current flows here, the voltage between those always remain zero, and for opposite current is protected by those diodes parallel to. Okay. Bakayım başka neyimiz var. Evet, bu şekli özellikle öğrencilerin kafasını karıştıracağı için kapsam almıyorum. Buraya yazdım. Bunu koyacağım slayta ama burada gördüğünüz gibi tyristörler single pulse'dan ziyade number of pulse uygulanır ve eğer devre LR network ise of course solution is obvious. Bakayım gelmiş bir solution. Vermiş tabii. Benim several times I solved that one. You remember this? Several times. For this case, your differential equation is I'm about to complete the course, by the way. Don't leave. I'm going to take another attendance list, and also I'm going to talk to you a few words about the examination. But Vs is equal LDI dt plus Ri. Therefore, Vm sine omega t is equal LDI dt plus Ri. So I is equal Vm over Z sine omega t plus k t over tau. Tau is equal L over R. Z is equal square root R square plus omega L square. And tangent phi is equal omega L over R. So the solution, I'm sorry bir hata yapmışım. Hatamı kim bulacak? Hatamı kim bulacak? Who is going to find my error? Şu artıyı sileceğim buradan. Niye yer açacağım kendime? Minus phi. So time omega t is equal alpha, current is equal to 0, initial condition. So K is obtained. Okay, so if you go to the next slide, you are going to obtain, it's a function of this one. You can see that K, that one is K here. This one is a second term, transient term, and that one is a steady state. This one is a steady state solution. That one is a transient solution. Okay. And then it's very difficult to obtain, by the way, it's very difficult to obtain the beta, the current final point beta here. You can see that this one is beta, is difficult. There's a chart over there. Probably he gives the chart. No, he doesn't give it. RMS value of output voltage. And you can see that this is the waveform. So alpha and beta. While the current is still flowing in thyristor, the voltage goes down to zero, unless the current becomes zero, thyristor remains on. You cannot put it off. Thyristor is a kind of semi-controlled rather, device. Bu kadar yeter çocuklar. Bu kadar yeter. Bence bu kadar yeter. 3 faz typical 3-phase AC controller. Not widely used now. Neyse ki kullanılmıyor fazla artık. Geç. Gerek yok. No need. So you are responsible from that kind of network, as well as you are responsible from this kind of network. Okay. Now, what am I going to talk? These are my final words. First of all, I was very much disappointed about your quiz 1, quiz 2, and also I carefully read your examination papers, the midterm examination papers, and I have realized that you are trying to find outside reference. Someone is helping you, and whoever he is, or ChatGPT. It looks like that. You also, some of you have already asked the answer of the question from ChatGPT, but ChatGPT made mistake, and those mistakes are covered. 2 examination papers are directly given from that part. So I still couldn't be able to decide what am I going to do that. But the rest of the students are already, they also inspired, by the way. So don't do that. Probably you can't do this from anymore, since it's going to be face-to-face examination. What I believe, and I'm trying to give you the message, is this: you have to try to summarize the cases. You have to clean your mind in summarizing the cases. What is rectifier? What kind of load I have? If load affects, yes, it does. What am I going to do? Ask you those questions. If it is a single switch, even might be a diode, might be a thyristor as well. If it's a single switch, what am I going to do? There's no second switch for negative part, so it's going to be only the first half wave. Load could be resistive, load could be inductive, load could be together, resistive and inductive together, or back EMF, electric motor example. So that whether it's a full bridge or half bridge, what kind of network I have? First of all, rectifier. Then second one, you never forget that MOSFET, IGBT, these are the switches. You put it on, you put it off. But thyristor is not that. Thyristor cannot be turned off unless the current is becoming zero, and then a tiny little negative current, then switch off the device. So while the current is flowing, whatever the voltage is going to transfer to the load side. Okay, so this is also should be remembered in your brief summary knowledge. You know what to do for DC to DC converters. We have buck type, boost type, buck boost type. So those types are peculiar phenomena. We have solved problems. You know the operation principles, and you know how to evaluate that one. Out, output values are evaluated. Input values are also evaluated. The ripple factor, form factor, and that kind of, uh, and also for rectification as well, we have those parameters. But mainly, if you have a non-sinusoidal AC waveforms, the Fourier analysis is necessary. I have already given the Fourier analysis. So do not come to the exam with a, of course, bring your books, notes, everything. But you have to clear your mind. Which knowledge, if a Fourier analysis is necessary, in which part I'm going to find it. For particularly inverter, output is square wave or quasi-square wave, single phase or three phase, which we have been talking today. Then for the inverter case, Fourier analysis might be required. I haven't prepared the examination questions yet. Therefore, I don't know what kind of questions you are going to face with. I wish you become successful. But as I told you, don't don't spread your mind in, you know, detailed knowledges. Just just try to summarize your brain. You concentrate on your brain, on the main topics and main subjects, and the how could I find during, I know during the exam lot of pages, you look at it and you couldn't find it. You find something, you think that it is not relevant. Try to understand. Please work hard and become successful. Okay. So before leaving the classroom, I'm going to take right is the last person. Abdul Bari Abdul Samet is the first person. I'm going to check it up. Don't leave, please. Don't leave. I haven't yet. I would like to see your names. Yeah, that's right. Abdul Bari is the first name. And right, let me see the right. Just a moment. Right. And the last thing I would say, if you look at the O-Learn, you can see your exam results. But in detail, you can open your examination paper and you can see my notes. I gave you some notes. Okay, you can see your exam paper as well. Okay, if you have any question, I'm here to answer. Otherwise, I'm going to say goodbye to you. I'm looking at the chat. Haftaya ders yok oğlum, okul bitti. Erdem. Önümüzdeki önümüzdeki hafta sınavlar başlıyor. Erdem, yanlış mı söylüyorum? Kasım sağ ol. Doğukan pardon. Evet. Ben de size teşekkür ederim. I also thank you for your effort. Okay. Bye bye. Thank you. I'm just leaving.